Okay, welcome back. We're very happy to have Michal talking to us about definable norms and Riemann-Zariski spaces.
Yeah, thanks for having me here. And I'll talk about. I have definable in the title, but it won't be with regards to minimality. But I thought that maybe I'll start with comparing my context of definable to the one that is more in the theme of this conference. So a lot of results that come from the interaction between O-minimality and Hodge theory started by Raynaud theorem, or Riemann-Zariski's conjecture, which was recorded already, but let me write it just so that we get in the mode. So if A is a complex abelian variety, where C and X is a curve of the genus bigger or equal to in A, it's closed subscheme, that is not elliptic. It's genus bigger or equal to. So then, if I take the torsion points A and I intersect it with X, this is finite. So this is the Raynaud theorem. Later calculated not only for curves, but in general with higher dimensional varieties. A higher dimensional subvariety has a Zariski dense set of torsion points if and only if it's a torsion translate of an abelian subvariety. Okay, so sort of these questions about interactions of torsion points and varieties and special subvarieties, and there are various approaches. Let me focus right now on two approaches. So O-minimal one and Equidistribution one. Okay, so this will be O-minimal first. So here the story roughly goes as follows. So I want to tell these two to compare some levels of generality. So 1983, this was Van den Dries. And then in 1986, this was Steinhorn. And this is where the notion of O-minimality as we use it today was extracted. Van den Dries was considered a very related notion. But as we define it today, this was here. And then in 1989, there was this Bombieri-Pila. They used the determinant method to count points in some transcendental curves. And later, in 1996, Wilkie proved O-minimality of Rx. Then Pila-Wilkie, this was 2006. This is point counting. If we have good O-minimal structures, you have this point counting, which was based partially on this determinant method. Then 2008, this is Pila-Czanier strategy. Which is the non-minimal approach to prove Raynaud theorem. Okay, and then I guess this conference is really what happened later. but yeah, so Raynaud's theorem is from 1983. It took 25 years by this strategy to give a new proof, but this new proof later gave very fruitful interactions. I want to talk about, so my talk will be closer to this equidistributional approach. So here it started with Arakelov in 1973 or 4. this idea of doing intersection theory on an arithmetic surface. And then Faltings in 84 developed some geometry in a paper called Calculus on an Arithmetic Surface. In the 90s, this geometry was generalized by Gillet Sulet. And then in 1995, Thoreau Jean came and he defined these adelic metrics on arithmetic varieties, which later allowed people, later some distribution results came in 1997. There was this Spiro, Ulmo, Jean, and below equidistribution theorems that I will mention. But then in 1998, Zhang and Ulmo at the same time independently proved Bogomolov conjecture. Bogomolov for Abelian varieties over number fields. Okay. Okay. So this is Bogomolov. At least if A is over a number field, generalizes the statement. However, later in 2000, Morivaki proved using similar methods Bogomolov conjecture that generalizes this statement. But a special point in this timeline that I want to focus on today is Yuan's result from 2008, where he proved. Okay, so maybe let me go here. So this is 2008. Yuan. He proved an arithmetic SU inequality. And this is a result from which you can deduce these equidistribution results mentioned here that are key to proving Bogomolov. So today I want to focus on this part and what does it mean to make this part definable. So it's somehow this line is O-minimality, and maybe later here people started proving that some things are definable in O-minimal structures. I want to focus on definability in this lower part, whatever it means. So maybe let me recall the Bogomolov conjecture. Proved by Zhang and Ulmo for number fields. So if A is an abelian variety over a number field, and H and T is in the Néron-Tate height, to say our number field is K, we can hook up this function called Néron-Tate height, and then it's zero if and only if a point is torsion. And then for a closed irreducible subvariety, that is not a torsion translate of an abelian subvariety, there is an epsilon bigger than 0 such that if I look at a set of X in X of K bar, such that the Néron-Tate height of X is smaller than epsilon, then this is not Zariski dense in X. So because Néron-Tate height 0 are exactly torsion points, let's generalize this Raynaud theorem at least over number fields. And then what Morivaki did is he defined Néron-Tate heights that use some extra data on finitely generated fields so that actually in Morivaki's the Morivaki version generalizes Raynaud theorem because you can just take a finitely generated subfield over which this abelian variety A is defined. Okay, so this is the Bogomolov conjecture, and I want to present this point of view that you can prove it by equidistribution. So maybe let me also hear about this phenomena, equidistribution. So in the way I'm formulated is due to Jean. So if we have xn sequence, let's stick in the number field case, so in the assumptions from the Bogomolov, let xn be a sequence such that no infinite subsequence is contained in a torsion translate of an abelian subvariety. And such that the Néron-Tate height of xn goes to 0. So then, after fixing an embedding of our field into complex numbers, the Galois orbits equidistribute towards the Haar measure. On AFC. So AFC is a quotient. It's a compact proof. It has a Haar measure, and if I look at these orbits via this embedding, I can take the probability measure where I just look at the orbit, I put Dirac deltas everywhere, I sum them, and I divide by the number of points. Then it's a probability measures, and these probability measures here, they converge, the weak star converge to the Haar measure on this compact abelian group. And so stated like this, from this statement follows, because if the Bogomolov conjecture was false, I could find a Zariski dense set of elements X such that the Néron-Tate height goes to 0. However, they have to equidistribute towards a measure that is supported on the whole variety. So in particular, such a sequence, it cannot be supported in some closed subvariety of the abelian variety. So this is the equidistribution approach. But this is Zhang's equidistribution, and I want to talk about this more general nuance and some engine behind it. So this nuance equidistribution is a bit more general. And it says the following. So let's take an integral projective variety over Z. So integral projective scheme over Z. And it's a normal. Let L be an ample line bundle on X. And assume that if I look at the complex identification of L, it's equipped with a Hermitian metric. So I have a norm on every fiber on the complex manifold X of C. So then let H L bar X Q bar R 0 be the corresponding height. So this height, maybe as a small remark, is defined in a way that if I have my point X in X of Q bar, it's defined over some number field k, but my x is projective. So I can assume that my x is defined over OK. And then this map from OK to X, I can pull back this data of this line bundle to this thing. And then I get some divisor here. I can take a section, I get a divisor, plus I have some data at infinity. But from this divisor, I can look at the logarithms of sizes of residue fields of points corresponding to this divisor. And from that, I can hook up this number, which is the height. Maybe I normalize by the degree of X, but I don't want to maybe get further into this. There is some height associated to such data. And then Yuan equidistribution says that if Xn is now a sequence of q-bar points, is a generic sequence such that, so it converges to the generic point, and such that if I look at these heights of Xn, it converges to some number that depends on this line bundle. And so this is, okay, I will write it like this, but this I will explain later. There is some arithmetic intersection theory here. And then we divide it by d plus 1 times the degree of X with respect to L. This is purely geometrical. If that's the case, then the Galois orbits of Xn equidistribute to the measure that can be defined as you take the Chern form corresponding to this Hermitian metric on the corresponding complex manifold. You take it to the div power and you normalize so that it's probabilistic by this degree. So by Chern-Weil theory, the weight of this measure is this degree. And this is on X of C. Moreover, one can also define counterparts of these measures on other places. So there is also some equidistribution of these Galois orbits on CP for each P.
Do you really need a good model over Z, or you can just work over Q and better imbue everything with p-adic metrics?
Yeah, you can work over Q, and then you need p-adic metrics. So this is partially what this is a theory that Zhang developed here, because you write that if you want to get, for example, Néron-Tate height, then you want to maybe allow for finitely many places where you don't have a natural metric, and you want to allow also for limits of such.
Okay, but at the end of the day, the theorem still works. You don't need any except okay.
Yes. Okay. Yeah. So okay. Okay. So this is Yuan's equidistribution, and since I want to focus on this arithmetic U and some generalizations, let me sketch how it's related to this theorem. But, yes.
Sorry, like the condition about the convergence of the point, of the height of the points, is like how much goes beyond the small points above, like because above they're like going to zero. Their Néron-Tate height goes to zero, right? So
yeah,
it goes to something like these are not small points, like
no, these are some small points. So okay, so Zhang proved that actually this is this bounds the essential infimum. So this actually, if you have a generic sequence in such a variety, the limit of this is always bounded from below by this number. But if it's actually attained, then you have this equidistribution. Although there are examples where there is no subsequence. So the essential infimum of this function, when you look at infimum over all generic sequence, can be bigger than this number. But Yuan equidistribution applies when this happens.
So there are still small points.
Yeah. I mean, this is usually referred to as a small sequence. Yeah, like that. Okay, but so this arithmetic U. What does it say? So to introduce it, let me give. Okay, so maybe here was the arithmetic U, and here will be geometric. SU inequality, the usual SU inequality. So usual SU inequality, I have X variety over some field, projective. I have A and B ample line bundles. So volume, by volume of A, I mean lim sup of the space of global sections of tensor powers, normalized so that it actually converges. So I take n to d, where d is the dimension of x, divided by d factorial, and then goes to infinity. And then SU inequality, in this language, it says that volume of A tensor B inverse is bigger or equal than some intersection number, namely A to D minus D times A to D minus 1B. Okay, so this is a theorem about sections of some line bundles that are differences of two ample, or one can also upgrade it to NEF divisors. And arithmetic SU is similar, however, we need arithmetic counterparts of these. So instead of volume, we work with arithmetic volume. So it's also supposed to measure the growth of sections, but this time we don't look at all the sections, we look only at small sections. So we take limit of the log of the number of these sections inside tensor powers of L that are small. So this check here means small sections. And small means that the sup-norm is smaller or equal 1. So a section, it has a norm at every complex points of x. And this is this is the intersection of the unit ball of the sup-norm of my Hermitian metric and this integral lattice. So it's a finite set. And then I normalize it by n to d plus 1 divided by d plus 1 factorial, where the same is here. So maybe I should write it. D is the dimension of the complex variety x of c, or d is the dimension of x over z. And d plus 1 is the absolute dimension. This quantity is actually bounded, and this one is can be used in this inequality by a related one, where I also take lim sup, but then above here I take something called h sup of L to m divided by the same thing. So here h sup of L to n. This is this is the arithmetic degree of the pair consisting of this lattice of sections and the sup norm corresponding from the Hermitian metric. And this degree is just minus log of covolume. So I have a lattice, I have a norm, I can take this lattice tensor the reals divided by the lattice. And if I take the Haar measure where the unit ball with respect to this norm has measure 1, then the volume of this quotient is the covolume, and I take minus log of that. Okay, yeah. So this inequality follows from Minkowski's theorem about lattices. Okay, so U1's SU. Says similarly as this one, that the arithmetic volume of, now I have two ample line bundles, so I'll explain the assumption in a second. And if I take the volume of this one, this is bigger or equal than some arithmetic intersection number. That is the same, but maybe it's shifted by 1 because, so here L and Ln are ample, and the Hermitian metrics are semi-positive. Okay. Okay. So this is a statement about existence of sections of some Hermitian line bundles, about existence of small sections, because this just says that given these arithmetic numbers that I have not defined, but I will, if this is big enough, I know that tensor powers of this line bundle have many sections that have small norms. Okay. Okay, and so why is this statement relevant for these equidistribution theorems? Namely, if I take here, if I look at if M has the corresponding trivial line bundle, then this intersection can model. So if M is the trivial line bundle, but the metric then corresponds to some continuous or smooth function, the corresponding complex manifold, then this intersection LB times M can be expressed as the integral of this function with respect to the measure that appears in the U1's equidistribution. So okay, so this is the rough relationship between these theorems. That's why U1's CU actually implies his equidistribution theorem. And okay, and so this is the statement I want to focus on making definable. So maybe the question is it definable in what size? And before I erase this, so maybe one could ask, yeah, why? So the motivation for this type of questions is that often if we are in this definable setup in some reasonable realm, then we can make things effective, or we can make things uniform. And there were various works recently on uniformity and effectivity in these Bogomolov statements, so notably Habeger, Gao, Kühne, and Gao, Ge, Kühne. And so this can be seen as one motivation, but also somehow another motivation is to give some applications for a logic theory that I'm studying, that I will introduce. This is the end of this technology, and why not upgrade it? And maybe let me remark that there are some results of this form making this SU inequality more explicit. So there is the work of Jit Yap. So this is in the case M equals O. So this is the relevant case for equidistribution. And he does have some applications of that. And then there are Van Bin-Luo's results in the function field case. So, but what do I mean by this definable? So to explain, let me focus first on the right-hand side. And let me define this arithmetic intersection product. So say for simplicity, let's assume that X is a subvariety of projective space over Z. We fix some embedding. So L is maybe very ample. So we just take O of 1 restricted to X. And we take as the norm, which won't be Hermitian here, but it can be written as a limit of such. And for those, I have a clean formula. So let me stick with the Weyl norm here. And let this be the norm. So what does it mean? So i.e. on the projective space, if I have a section corresponding to the linear form AI xi, then the veil norm of this section at a point of a projective space with variables z0 to zn, this is just the absolute value of AI zi divided by maximum of absolute values of zi. So usually for this to be Hermitian, as opposed to putting maximum at the bottom here, one could put the sum of zi squared and the square root of that, and this would be the Fubini-Study metric. But here I somehow want to use this veil, which is not Hermitian, but it can be written as a uniform limit of such. Okay, so I want to define these intersection numbers using this data, and here let R of lambda 0, lambda d, where d is the dimension of the generic fiber of X, be the resultant of this variety. What does it mean? So, which means that it's homogeneous of degree equal the degree of X with respect to L in each variables lambda e, which is the tuple lambda I0 up lambda IN. And it's such that if I put here some, say, complex numbers, or in any field, extended in any field of characteristic 0, a tuple like this is a 0 of R if and only if the generic fiber of X intersects all hyperplanes defined by linear form defined by these coefficients. So I want to write sum of ij, x, j. And here j is from 0 to n. So each lambda I bar defines a hypersurface in my projective space, and then I take d plus 1 hypersurfaces. So maybe I mean P3, I have a curve, and if I take two hypersurfaces, usually I expect the three things not to have a common intersection, but if they do, there is a single polynomial called resultant that captures that. Okay, and then this polynomial, okay, it's some polynomial with some variables, so I can write it. Let's write it just like this. It's a sum of some AIs times lambda i's, and then I put R1 is the veil height of this tuple AI. So I look at just coefficients of the resultant, and I take veil height of that, which I think it was introduced on some previous lectures. And then, okay, so this is not exact. So this number is not exactly this number, but it's very close. So if I take the same number but define after taking composition with the Veronese embedding, with higher and higher Veronese, I will get the arithmetic intersection number. So if FM is the same number after replacing X inside Pn with X inside Pn, and then doing M Veronese, which will give me a new embedding into some projective space of higher dimension, then this arithmetic self-intersection can be defined as a limit when m goes to infinity of Rm divided by m to d plus 1. Okay. Okay, so here now I can say what do I mean by definable. So the point is that this number is defined as a height of a tuple coming of a tuple of elements of the base field over which I'm working with. So here in this case, these will be rational numbers or even integers, but I could imagine this over any field of a tuple coming from geometry. So maybe more precisely, if K is a field equipped with a global height, so global height is a tuple of functions Hn from projective spaces of K to non-negative real numbers and satisfying some axioms. Let me quickly write them. And here I don't write which n I take. So height of 1 is 0. Height is permutation invariant. Height of longer tuples increases. Height of Segre product is additive, even of different lengths. And the triangle inequality, height of the sum of two vectors. So let's say one of the entries here is not 0, can be bounded by the height of the connection of those plus height of 2, 1. Okay, so more precisely, if K is a field equipped with such data, the formula if K is a field equipped with such data, if I have an embedding of a variety over my field into a projective space, and then this limit of Rm divided by d by m to d defines good intersection product. For example, it will be linear with respect to the Segre product. If I have two embeddings and I take Segre, I will get the multilinear expression that you expect if you define this as j to power d plus 1.
So this global height is like a sequence of heights, right? It's a sequence of heights.
Yes, so this is for each n bigger or equal to 1. Yeah. Yeah, okay. So in this sense, here in this formula, the right-hand side is definable, but now what about the left-hand side?
Sorry, question is this for, is there supposed to be some base change operational lag here too, if you pass to a cubic section, or is it directly close to start out?
No, so here K is, I think with the resultant, it will have just, the resultant will just have K coefficients. Yes. So if the height lives on K, yeah. So maybe here there's one subtlety. This resultant is only defined up to scaling, but because we take the height, and height is also defined with respect to the projective space, if you have such data, you can define it.
But ultimately, your sequence will be defined over a larger field.
In my sequence of points that I want to apply equidistribution, say? Yes, yeah. So okay, so actually, I mean, here with these heights, one has to be a bit careful. So because it may not be the case, it is the case for rational numbers that that this function, this data is essentially unique. So it will be unique only up to scaling, because if you multiply all these heights by 7, they will also be satisfied. However, on Q or on number fields, there is a unique such height, so we can talk about points valued in the algebraic closure. But for more general fields, it might happen that you have a finite extension where you have 2 possible extensions of the heights. Okay.
Answering one more question. I don't understand, what do you mean? It's fine if you haven't said this yet, but by the word definable, you said, so this is definable now. Do you literally mean it's expressible in terms of some data, or do you mean something else?
Okay, so I guess, maybe I'm doing some double game here. I'm trying to say, I mean that there is some reasonable formula with uniform convergence that you can bound the error, which I haven't said here, but you can actually do it. But it's equivalent to being, in this case, definable in some continuous logic theory.
Right.
That I don't want to talk about,
Yeah,
but
okay.
but this is
Okay.
Okay. And so maybe it's worth to say that, okay, so maybe let me give you a few examples, because this data maybe seems to be not that easy to make, because you have to define height for every projective space. But for k equals q bar, these are Weil heights, absolute logarithmic Weil heights, and this is the only one up to scaling. And you also have these Morivaki heights. Finitely generated fields. But just to have maybe one more example, the function field case, if k is the algebraic closure of k of t for some base field k of any characteristic, and I have some couple of rational functions. So maybe they are not in k of t, but maybe they are in k of c for some smooth projective curve over small k. Then I can define the height of this tuple by taking some normalization. And I take the sum over closed points of my curve of minus minimum of order of vanishing or at C of Fi times the degree of C over K. So this will also define such a data. This is the function field case, and on fields of higher transcendence degree over some base K, if you have a polarized variety, it will also define such a data. But it won't be okay. Maybe. So this one again is unique. If you unique up to scaling, these heights are unique up to scaling, satisfying these axioms. If you want them to be literally 0 on small k. Okay, so these are some examples. Okay, but so I guess really what I'm aiming at is whether one can express this side as a height of some data corresponding to embeddings in the projective spaces that may be defined as L bar and M bar. And here maybe so actually to analyze this left-hand side, what will be important is some representation theorem here. So this is by Beniakov, Destik, Shosky, and me. And so it says that for each global height on any field, there is a measure mu, a regular Borel measure on the space of absolute values, multiplicative triangle inequality, and norm of 0 is 0 if and only if the element, norm of an element is 0 if and only if it's 0, such that this height of the tuple is given by the integral with respect to this measure of log max of absolute value of xi's with respect to the measure. So this is the measure on the space of norms, and here I integrate over the space of norms. So this is how usually the veil height is defined, but okay, this is the realm with that. And now I can talk a bit more about definability.
Sorry, MK is the space of norms.
Yes, yeah. Of the left-hand side. Okay, so here I want to do some adelic geometry on any field, and one way. So maybe here you can see that one way to do it is via these axioms. This maybe some proposal, but it's somehow equivalent to doing some measure theory on the space of absolute values. But the way these volumes are defined, I mean, they're defined highly non-uniformly with respect to norms. So here I just look at the global sections, but if my field is bigger, one would have to have some proper generalization of small sections. And so actually for any field, this is better thing to generalize, this covolume of a lattice. But to do this, one has to look at things more uniformly. So let me maybe okay. So let's say for what kind of data we'll consider this left-hand side. So let's say that X be a projective variety over K, and let's say we have some J0 that is an embedding into one projective space, and the J1 is an embedding into another projective space. One, and I want to consider. I want to say that these two line bundles, they are fullbacks from these two projective spaces of these veil metrics over all places. So okay. So what does it mean? How do I want to interpret this left-hand side? So the first step is that if I put L be J0 of O1 minus J1 of O of 1, we define norms, the supreme norms on the space of global sections of L for each norm on K. So this is just an element of MK. And somehow this is how we will globalize this data. Okay, so this is maybe, I like this phrase that I think from Alex's talk as democracy of Shimura varieties. So here maybe this is a more like just adelic approach, but would be democracy of places. So the point is that this formula for the veil metric works over K with this particular absolute value. So if I have a section on Pn of O of 1, I can measure its norm if my base fit is equipped with some norm, just by looking at the norm of the evaluation divided by maximum of norms of coefficients. And so those for S, which is a section, maybe it's some local section of this line bundle L. If this S locally, I write it as A tensor B inverse. I can define the norm of S to be the norm A times norm of B inverse. And so this defines norm of for each place on K, we get a norm on sections of this line bundle, and then we define the sup-norm to be the supremum over X in the Berkovich identification with respect to this norm V of values of this norm. So this is really supremum of expressions like here over points that belong to my variety inside fields that extend K with the associated with the fixed absolute value. Okay, so using that, doing that, we get the following object. We get this finite dimensional K vector space, and we get a family of norms for each absolute value in K. And if our field is equipped with these heights, we can define. Maybe this is step 2. We can define the degree of this family, of this data, to be the integral of minus log of the determinant absolute value with respect to a measure on the space of places that we choose. So this is where omega belongs to the determinant line bundle, the determinant, the copy of K of this H0 of XL, and the norm, the determinant norm, is defined as infimum. So we have some V going on here. It's the infimum over omega. We write it as E1 times EK. We take the product of the sub V norms. Okay. Okay, so this is some formula for the degree that is somehow natural from this measure theoretic point of view. This approach is one developed usually by Chen and Morivaki. In the context of so-called adelic curves, and but somehow to understand, using this definability approach to give some applications for potentially for this type Bogomolov type questions and working over in families. Theoretic formalization is a bit awkward, and so it would be nice to geometrize it, because this is also not definable in the previous sense. I mean, this is a formula that does not use these height predicates of things coming from geometry, and so yeah. So somehow, okay. So here definability means that I'm interested in this kind of formulas, but I would like to present them in a different equivalent way, where I just count heights of some polynomials, essentially. So to understand better this formula, we do some geometrization. Namely, really what we are looking at in this picture is we have some variety over K, but now I somehow look at this data from the point of view of all places on K. So I can replace this K by the Riemann-Zariski space of it, which will capture all of these valuations. So it can be defined, well, in two equivalent ways. So one is I can take the inverse limit of all, say, projective schemes over Z that have K as a function field. So assume it's finite type. So this is Riemann-Zariski of K. And then above, the relevant space to capture this kind of metric data would be the inverse limit of models of X over K, but over some S. So this is what I will call Riemann-Zariski of X over K. Yeah, so okay, so here these are projective integral schemes over Z with function field K. And here I take models over some S such that the following diagram happens. Or it is a full. Yeah. So I have these Riemann-Zariski spaces, and really this data of mapping projective spaces with this function defines of given amount from X to N over K. And if I have, okay, and as the model of K, I can get the canonical model associated to this data, which is just the Zariski closure of X inside PNS. And I can look at the line bundle on this guy, and this gives me a line bundle by going to the inverse limit on this Riemann-Zariski space of X over K. And so the way we understand these formulas with Nuno and Antoine is by looking at, yeah, so we have a line bundle, call it epsilon, on this Riemann-Zariski space. Then if X over S has geometrical fibers reduced, then sup-norms are calculated by fibers by stocks of pi star epsilon, which we prove is a vector bundle. And we can pass it, and we pass it. Okay, so somehow to prove that this push forward is a vector bundle, we decompose this inverse limit into ones where the base varies and where we blow up the fibers. And then using this formalism, we can get some nice formulas for these kind of integrals that before were proven measure theoretically. And so we do prove that the left-hand side is definable in some sense. And maybe I'll finish here.
Any questions?
Yeah, so maybe I missed that part maybe, but for in Yuan's arithmetic too, you define both sides of inequality. And so would you then impose the fact that the inequality holds as a property of your structure, or is there some way to deduce it from underlying?
No, so actually I don't know yet if it holds for this more general definition, but I'm rather convinced that it's a good definition. So, and this is because, okay, basically, so really I'm interested in this kind of SU inequality for these structures, because basically, if you could prove this generalized SU inequality for these structures, it would imply decidability of the theory of algebraic numbers in this language. So you could say there would be an algorithm that would say whether an equation in algebraic numbers, if you add some height conditions, whether it's solvable or not, if the height conditions are open. And but so this definability part here is rather soft. Like somehow the point is to have a right formalism to talk about these things. But it implies, for example, that the statement over all these objects should be equivalent to an arithmetic SU with a uniform error. So in this, when you take the volume, you divide by some powers of n, and there is some error, but this error is not known to be uniform, say in families.
Yeah. Other questions? Okay, now let's take Michal again.